Welcome back to the video series on integration and differential equations. Today we're going to take a look at partial fractions. For our example today, we're going to evaluate the following integral, and I want to take a look at this expression inside the integral. This is a rational expression, meaning it's one polynomial divided by another. And let's specifically look at the denominator. So we've got two factors there in the denominator, the x minus 2 and the 2x plus 1. So here's how the partial fractions method is going to work. We're going to take our rational expression, x plus 4 over x minus 2 times 2x plus 1, and we're going to rewrite it in the following way. So we're going to write it as a over x minus 2 plus b over 2x plus 1. And in this context, a and b are real numbers. And what we're doing here is called the partial fractions method, or just partial fractions. All right, now our next task is to solve for a and b. So let's take this expression here and let's multiply it through by the common denominator. So I've just recopied the entire equation here and multiplied through by x minus 2 times 2x plus 1. So on the left side, the entire denominator cancels. On the right side, we get a factor of x minus 2 canceling in the first term, and then a factor of 2x plus 1 canceling in the second term. So what we end up with is a much nicer looking equation. X plus 4 equals a times 2x plus 1 plus b times x minus 2. So we'll call this the master equation, and we're going to use this to find those numbers a and b. We're going to plug numbers into the master equation that make a term equal to 0. So let's try to understand what that's saying. We'll look at the right side of the master equation, and let's try to make one of these terms here equal to 0. So let's start with, say, making the x minus 2 equal to 0. Okay, so what x value is going to make that happen? Well, that would mean x equal 2. So let's plug x equal 2 into our master equation and see what happens. On the left side we get 6, on the right side we get a times 5, and as we designed here, x minus 2 is going to be 0, so that second term there is just 0. Okay, so that allows us to solve for a really quickly. That's saying 5a is equal to 6. In other words, a is equal to 6 over 5. Great. So let's try the same thing for b. Let's see if we can figure out the value of b. To do that, we would like to make this term here equal to 0. We want to eliminate the term with the a in it. So if we wanted 2x plus 1 to equal 0, solving for x, we'd have 2x equals negative 1, or in other words, x equals minus 1/2. So that's the value that we're going to plug into the master equation. All right, so looking back up at the master equation, we've got minus 1/2 plus 4 is equal to a times 0. Well, we know that 2x plus 1 is going to equal 0 because we designed it that way. And then moving over, we've got plus b times minus 1/2 minus 2. All right, so going through the algebra here, on the left side we've got 7/2. On the right side we've got b times negative 5 over 2. Okay, and in order to solve for b, let's multiply both sides by negative 2/5 here. So multiplying by negative 2/5, and we get on the right side, we just get b. On the left side, minus 7/5. All right, so we can conclude that b equals negative 7/5. So we've now got values for a and b, and we're going to go back up here to our original partial fractions expression here, and we're actually going to plug in these values of a and b. So let's do that. So normally what I do in order to keep things flowing logically is at the beginning of the question I just put a star at this partial fractions expansion, and then once we've found a and b, then we can say something like, from star we now know that our original rational expression is equal to a, which is 6/5. So I'm just going to say 6/5 times 1 over x minus 2, plus b was minus 7/5. So why don't I say minus 7/5 times 1 over 2x plus 1. So what this allows us to do is to rewrite the original rational expression in the integral. So now we're going to be able to do the integration portion of the problem. So now we can say the original integral in the problem is equal to the following integral, and we're just going to replace the original rational expression which we had with now this new and improved expression. So the idea is that we couldn't integrate the original rational expression directly, but now that we've gone through the partial fractions approach, we can go through this integration very quickly, and it will be especially helpful if you looked at the shortcut that we discussed in the previous video. So each of these terms inside the integral is now in ln form, and we can write down the value of our integral. So we're going to get 6/5 times ln absolute value of x minus 2. And when we integrate the second term here, we're going to have to be a little bit careful when we apply the shortcut because the coefficient of x is 2 here. So integrating, we've got minus 7/5 times, it's going to be 1/2 ln absolute value 2x plus 1 plus a constant, and the half here coming from the shortcut that we discussed in the previous video. Okay, so just cleaning this up a tiny bit, 6/5 ln absolute value x minus 2 minus 7/10 ln absolute value 2x plus 1 plus c. So we have used the partial fractions approach to take this integral, which we could not compute directly. We were able to rewrite it in this form here, and then it was just a matter of applying our ln form to get the expression integrated. Now, depending which resource you're following, you may leave your answer like this, or you may simplify the answer using the ln form. So I'm now going to show you the steps that we would go through if we wanted to do the simplification. First thing we do to simplify this is we would create a common denominator. So we'd take this 6/5, multiply it by 2 over 2 to make that 12 over 10. And what that would allow us to do is actually pull out 1/10 from this full expression. So that would leave us with the following. So I've just pulled out the 1 over 10, kept the numerators times the ln expressions, and then we just keep the plus c at the end of the expression here. Next step would be to use the power rule for ln. If you're not feeling too comfortable with these log rules, then you can go back and watch the review video on log rules. So there we've applied our power rule. Next up, we could use the product rule for ln. Here we've applied our product rule for ln, so we've now got a product sitting inside the ln function, and 2 more steps to go. We can use the negative exponent to bring the 2x plus 1 factor down into the denominator, and then very last step is just to create a single set of absolute values. So we can use the absolute values as brackets to be clear that ln applies to everything inside the absolute values. And there we have our very final answer. Lots of good practice with partial fractions as well as with log rules. Thanks for watching, and we'll see you in the next video.